Go. My slide says chapter 6. It's coming out of your book, chapter 5. Thermochemistry. What do we mean by thermochemistry? By now we should have a pretty good idea of what chemistry is. Thermo just focuses on heat. Most reactions either evolve heat or absorb heat in the process. But theoretically, if you have the same amount of energy contained in your reactants as your products, you could see a net zero change in heat. Okay, so what do we mean by energy? Actually, this is a physical definition. So chemistry borrows from physics. Capacity to do work is the first possibility for energy, or to produce heat. So what do we mean by work? Well, the work function is a force acting through a distance. Right? So if a force is applied to an object and it moves, then some work is being done. But if I push on this wall, a force is being applied, but nothing's happening. No work is being done. But if I push on that wall and expend energy, I am converting that energy to heat. If it's not moving something, then the energy I expend is becoming heat. Okay, so that brings us to the law of conservation of energy. All that says is for the entire universe, energy cannot be created or destroyed. It can only be converted from one form into another. Now, for chemists, that's pretty accurate. But for physicists, energy can technically be converted into mass and vice versa. That requires a nuclear reaction. So the law of conservation of energy is actually, that one is the first law of thermodynamics. So for the whole universe, change in energy is zero. And that's what the first law of thermodynamics says. Okay. So we can take energy and divide it in for convenience and for discussion and problem solving. Energy can take two forms. Basically, it can either be potential energy, which means it has the potential to do work or produce heat. And if that's the case, then it can also come in two different forms. So potential energy can either be as a result of composition. And for chemists, that's energy stored in molecules. For instance, nitroglycerin. Nitroglycerin has a lot of energy stored in its bonds. And all you have to do is, by accident or design, disturb it just a little bit, and it will release that energy. That energy is part of its composition. The other way that energy can be potential is by its position. So and that requires that the object and its position be in a gravitational field of some kind. So at the surface of the Earth, an object has a certain amount of energy, but if you raise it in that gravitational field, if you apply a force against the gravitational field and increase its height, then you have added energy potential energy to that object. So it may start down here, move the object up to here. It has gained potential energy due to its change in height. And all you have to do to find out how much that is let it drop. And it will gain velocity until, of course, it's ground. What is it they say? It's not the fall that kills you, it's the sudden stop at the end. Or the guy that's passing the windows up in the skyscraper. Everybody notices as he was falling. So far, so good. That's potential energy. Objects can also have kinetic energy, and that's based solely upon motion. So kinetic energy can be calculated for individual objects, even as small as subatomic particles. They can have kinetic energy. Your book might say that. Preference in how you write it. But how you calculate it is fixed. So the mass of the object times its velocity squared gives you the kinetic energy. And the units of measure here are joules. Okay? So, and the interconvertibility of units of measure requires that joules be equal to kilograms for here, right here, meters per second squared. So kilogram meters squared per second squared is a joule, in case you need to make conversions requiring canceling these units rather than that unit. Okay? Now let's go back to potential energy. The potential energy of position. In this little thought experiment, we have one object, and they appear to be the same size, same mass, and that's a fair assumption. This one has more potential energy than that one because it's higher. If we release this one and it strikes this one, then if the collision is perfectly elastic, then all the energy of this one will be transferred to that one. And where should it end up? Back up here, right? Same height. But in reality, when that happens, the second ball only ends up here or at some level lower than that. And the reason for that is that the transfer of energy is not perfect. In this case, it's not completely and perfectly elastic. So if this now only has a portion of the energy that A originally had, where did the rest of it go? Well, it was lost to heat by friction. Okay. That just illustrates the point, tries to illustrate the point that energy is not created or destroyed, it's only converted. Part of it is reconverted into potential energy and the rest of it is heat. Okay, so when we talk about chemical reactions and measuring the energy either produced or absorbed by a reaction, the way we get a handle on that, the way we quantify it, is with a difference in temperature. Right? And energy is always transferred spontaneously speaking. Energy is transferred spontaneously from high temperature to low temperature. And the only way you can get it to go the other direction is to couple the process with another process that converts energy and drives the movement of energy in the opposite direction. It's kind of like a reaction that's can go both ways. It can go this way and go that way. It prefers to go this way, for instance. But you can drive it backwards if you couple it with a reaction that will put energy back in and make it go that way. So that's how we air condition our houses, our cars. Normally what happens is heat tends to enter the car in the summer or leave the car in the winter. That's the spontaneous direction. Okay, I mentioned force acting through a distance, that's work. And now the two different concepts. One is the state function versus the path function. So at this point, let's just get a general idea of what that means. The state function is any function that describes, or a property that describes the situation as it is right now. What is its current state? It doesn't matter how it got there or where it's going afterwards. This is just what it is right now. Whereas a path function depends on the path that the process took. It went from here to here, over here, over here, back over there. It might come back to the same place, but a path has been taken and a change has been observed. Whereas a state function, if you do that, then it doesn't care. You may have gone way out here and come right back to this one spot. In a nutshell, that's the description for those two. Now, various quantities that can be measured or calculated for in thermochemistry. Some of them are path functions, some of them are state functions. Okay, some more terms that we need to define. What is a system? A system is whatever you define it to be. Okay. You can define your system to be the entire universe, in which case your system is everything there is. But if you define your system less than the whole universe, then your system is within your limits or within the limits of the problem as defined for you. And everything else around it is surroundings. Okay? Now, certain things can be transferred between them depending on how you define the boundary between the system and surroundings. Let's suppose we say both matter or mass can be transferred between the two, and heat can be transferred between the two. In that case, we have an open system. Open systems exist, but for our purposes, they're not very useful. Because if you can't control what's happening backwards and forwards, then you really can't do anything about it. What if we restrict the transfer to just heat? Right? So we're not going to allow matter to transfer, only heat. That's a closed system. It just excludes the transfer of mass. And if we restrict our system to a boundary that will allow neither matter nor heat to transfer, that's an isolated system. Like a styrofoam cup with hot chocolate or coffee in it. You don't allow, well, that's a bad example because once you start sipping on it, you transfer matter. Let's say you hold it in your styrofoam cup and you don't, it's too hot right now. Right? So until you start sipping on it, it's an isolated system because that styrofoam both contains the liquid and does not allow heat transfer. Sort of a bad example, actually. Okay, so energy and matter can be exchanged in an open system, only energy in a closed system, and no exchange in an isolated system. We're going to take advantage of the isolated system when we do our calorimetry experiment. That'll be the one after Boyle's law. We'll do Boyle's law next week, and then the one after that will be calorimetry, in which we use an isolated system. Okay. So now that we have our system and surroundings defined, sometimes it's useful also to limit our surroundings. So our surroundings might have limits also. And in that case, we actually don't want a porous boundary. We want this whole thing to be isolated. If we're talking about system and surroundings, if the surroundings includes the entire universe, what's left over from our system, then we could refer to any change in energy for the system in terms of the universe. But if we restrict our surroundings, then we refer to the change in energy as just total. I view those as two different things. The authors of your book might conflate them both, but I think it's difficult to support that view. Okay, so now that we've got our boundary established, and first part of our discussion is only going to be in terms of heat transfer. Everything, now when heat moves, it's going to have a sign, either positive or negative sign. So we need to define what is the positive, what does the negative mean. And those signs are always referenced to the system. What does the system see? If the system sees heat coming in, that's a positive value. Okay. If the system sees heat leaving, that's a negative value. So for heat or energy entering, that's a positive value. And it's also termed endothermic because it's moving in. Endothermic. Whereas if it's leaving the system, it's a negative value, and it's exothermic. And in the process, the surroundings gain this energy, and here the surroundings lose energy. But it's all referenced to the system. Okay, so when we're, let's see, is the freezing of water endothermic or exothermic? Well, what's our system? It's the water that's turning from liquid to solid, right? So in order to do that, it has to lose energy, doesn't it? Right? So that's an exothermic process. Define the system, define the surroundings, and which way is the heat flowing. In this case, it's exothermic. Let's see if we can classify each one of these. For convenience, the system has been defined for us, each one of these. So if your hand gets cold when you touch ice, in terms of your hand as the system, heat is leaving your hand, isn't it? So that's an exothermic process. If ice gets warmer when you touch it, the ice is the system in this case. And if the ice gets warmer, it's endothermic. Water boiling in a kettle, the water in the kettle is gaining energy in order to boil. So that's endothermic. Water vapor condenses on a cold pipe. The water vapor that's condensing is changing from a gas to a liquid. And in order to do that, it has to lose energy. So it's exothermic. And ice melting, if it goes from a solid to a liquid, it has to gain energy. So that's endothermic. Okay. Let's, in this case, we're given situations that require us to define our system. Sometimes there are good ways to define a system and poor ways to define a system. And how you define a system determines whether you can get the right answer. So when we say methane is burning in a Bunsen burner, the Bunsen burner actually only provides the mechanism for containing the elements of the system. And the system, if we're going to burn methane, we've got to have methane and oxygen both, or air, together. So the flame itself, during the process of burning, is the system. So when it does that, all the surroundings are getting warmer, right? So it's losing energy. It's exothermic in that process. What if water drops sit on your skin after swimming and evaporate? Right? So the water drop itself is the system. And if it evaporates, it has to gain energy, which makes it endothermic in order to gain enough energy to evaporate. Okay, we know that hydrogen gas and oxygen gas, when they're mixed together and ignited, they burn violently. That's how we used to send the space shuttle into lower Earth orbit. Well, along with some solid rocket boosters, but that's a different reaction. But when it happens, let's see. Let's put it up here. So we're combining hydrogen gas and oxygen gas, and it produces water. Under standard conditions, it would be a liquid, but under these conditions, it's probably a gas. It's still pretty hot. So let's see, we'll balance it as 2 here and 2 here. Okay. So the concept here is learning to think in terms of what's the energy content on this side and the energy content on that side. Okay? And which one has the lower amount of energy? If we define the system here, and we know that it's releasing energy, it's exothermic. So when you look at a reaction equation, it's helpful to view the energy as a reactant or a product. If it's exothermic, then the heat is on the product side, right? Giving up that energy. Another way of putting it is that energy that's now on this side, we could put an E there, but that's okay. The energy that's on this side used to be contained within these molecules. Right? So the higher energy was on this side, and the lower energy relative to the product only is on this side. And the difference is this amount that's released. Okay? So the water has the lower energy content. And that's one of the driving forces for a reaction. because the lower the energy, the more stable. So once you get it over a little hump called activation energy, then it spontaneously goes to that side because it's lower energy and more stable. Okay, so thermodynamics is a very broad area of, well, sometimes physicists claim it and sometimes chemists claim it. So since we're in a chemistry class, we'll claim it. And this first law of thermodynamics, as I mentioned earlier, is the law of conservation of energy. And it just says that the total amount of energy in the universe is constant. We just move it from here to there, changes form. And there's a second law and a third law, and actually there's a zeroth law. I guess they figured once they got the first, second, and third, they said, wait a minute, we need another law. So, but it's not the fourth law. It needs to go before the first one, so they made it the zeroth. We may or may not get to that one. Certainly not in this chapter. So now that we've got our concept of system surroundings defined, then we can talk about the system in terms of what is its internal energy. How much energy does it have? Or more precisely, how does its internal energy change? Because the only way you can measure absolute value like that is to compare it to something that's absolute. And by that, I mean an absolute zero. So what we do is we discuss it in terms of how has it changed from this state to that state. And we only need two factors to define and describe the internal energy of a system. We just need heat, which is designated by a little q, and work. More properly speaking, we probably should say delta Q and delta W. But none of the authors do it that way, so I'm not going to do it that way. Any change in heat and a change of work will define a change in internal energy of our system. Okay? And the same sign conventions are used for either one of these. Right? So if heat moves into the system, it's positive, moves out, it's negative. If work is done on the system, it's positive. And if the system does work on its surroundings, it's negative. Okay.
The first law of thermodynamics gives the relationship between the internal energy of a system and the energy flow into and out of the system. This example shows a system where heat enters and work is done by the system. Internal energy remains constant if there is no friction. If instead of adding heat, we do work on the system by compressing the piston, then energy will flow out of the system as heat. The internal energy is again constant. Take note of the sign conventions for Q and W. The signs of Q and W are positive when energy enters the system. Here we have a system in which a chemical reaction is taking place. What are the signs on Q and W in this example? Is there a change in internal energy?
Okay, what they're saying is this could be zero if our system allows for a balance between the two. So if heat is entering the system, but the system is doing work on its surroundings, this one's positive and that one's negative. And if the magnitude of those in that situation are equal, then there's no change. And vice versa. So when we're talking about these values, The quantities are given in terms of the magnitude of the change, right? How big is the number, and what's the sign? They left out the units of measure because the units of measure are always in terms of joules. That's the standard to measure for either work or heat and energy. Now, sometimes the process that's taking place can produce a huge amount of energy. So what we may have to do to keep the number from getting too big is stick a K in front of it for kilojoules. That just means 1,000 joules. So you may see that one also. Okay, let's see. I think we're still beating the horse, even though it's already dead. Endothermic process, the Q is positive, right, because we're adding to the system. Q is negative for exothermic. Got that covered. If the system is doing work on its surroundings, then it's losing work because it's donating that work to the surroundings. It's negative. And if the system is having work done upon it by the surroundings, then W is positive. Now, how do we measure these values? The most convenient way, at least in the beginning, to get a handle on what's happening, is to consider a confined gas with a piston, a frictionless piston, and define the work in terms of moving that piston, right? So if this is the initial state, this is the final state, what's happened? The gas is allowed to expand. So what it's actually doing is work on its surroundings. Right? It's expanding under a constant pressure. So if we say work is equal to force times distance, then if the pressure is constant, then that force can be in terms of pressure equals force per unit area, right? So force is then equal to pressure times the area of the piston. Okay, so that's where that term comes from. We can substitute pressure times area in for F. And in the process of this applied pressure and the movement of the piston, we're actually not just changing the height, but we're changing the volume. Right? So a change in volume, since the area is constant, we have that area times a change in height, or just H, whatever the measured H change is. And that's a positive value, area is positive value, pressure is positive, and area is also positive. So this distance traveled is that H, right? So we can substitute the D for that. And then if we solve for D, that's change in volume divided by area, and we can substitute this one in here also. So what do we get when we do that? Work equals P times A with a force, and then times change in volume over area. Okay. This is in the denominator, numerator, they cancel. So what we actually get is P delta V. If the P is constant, right? If we allow the P to change, then the P has to come in here as a changed value as well. So there it is in animated form. So work is equal to constant pressure times change in volume. And that's how you would calculate for a gas that's allowed to expand. Okay. Okay, let's see. The problem is, if we're going from here to here, then what's happened? Is it work on the system or work by the system? It's work by the system on its surroundings, which means it's losing. And the sign for W needs to be negative to abide by our convention. But the pressure is constant and the change in volume is positive. It's increased, right? So this is positive, and a negative can't be equal to a positive, right? So what we have to do is introduce a Fudge factor, which is a sign change. So that means when we actually use the formula, it's negative P delta V. Okay? Remember, anytime you have a delta actually doing the calculation, in this case, it would be the final volume minus the initial volume. And the final volume is larger than the initial, so it's a positive value. So that's where the negative comes from, right? On the next slide. Here we go. Now, if you ever have to, in this case, pressure, if we use pressure in atmospheres and volume in liters, we have liter atmospheres as our units of measure for work. And if we're comparing systems, this system compared to that system, we use the same units of measure, that's okay. But if we're going to try to equate work to a change in energy, heat, we need a conversion to joules. So this is your conversion. If you actually calculate liter atmospheres here, but you need to equate work with some sort of energy transfer, then you have to convert this to joules, and there's your equivalence, right? So remember, anytime you have an equivalence, you've got a conversion factor. Okay, so what's next on the agenda? Oh, a little quizzy. A gas expands against a pressure. Okay, so the gas is expanding, and the work calculation for A would be negative pressure, say pressure 2 atmospheres, times final minus initial. So it goes from 1 to 4. Final is 4. Initial is 1. There we go. So what do we have here? We have a negative. 2 times 3 is 6, right? 6 liter atmospheres. This is a case where we're going to compare these two, so we don't have to change it to joules, because they're both going to be the same units of measure. We just want to say which one produces or performs more work. So for the second one, W equals 3 atmospheres. So negative 3 atmospheres. Then the final volume is 3 and the initial volume is 1. That's 2 times 3 is 6. 6 liter atmospheres of work. So they're both the same. It's the same amount of work that the system did on its surroundings, right? Because the convention is negative. Okay. So let's see if we can confuse you even more with this one. Determine the sign of delta E. So what do we mean by delta E? Equals to Q plus W. Right? So delta E is Q plus W. And for the first one, this is an endothermic process. Endothermic process. and it performs work on its surroundings. So an endothermic process says that Q is positive, right? Q is positive, and performs work on its surroundings means negative. So the work is negative. Okay? In the first scenario, the absolute value of work exceeds heat. Right? So work is greater than heat in absolute terms. So the magnitude of the value is bigger for this one than that one, which means if this one's positive and that one's negative, then this one wins, and delta E is positive for that situation. The second scenario is just reversed, right? If this value, absolute value, is greater than that one, then the work, the negative, wins, and delta E is negative. So in this case, we have actually increased the internal energy because it's positive. In this case, we've decreased the internal energy of our system. Okay? So the other possibility is work is done on a gas, right? So work is done on the gas, which means it's positive, right? Positive. And it's exothermic. So Q is negative. Now in this case, if work is greater than heat, then the heat is less than the work, and the total amount is negative. So in that case, the internal energy goes down. And if we go the other direction, work is less than heat in absolute terms, then the positive is greater than the negative, and the internal energy increases. Okay? So those are just various scenarios, 4 different possibilities. It depends on what type of process is it for heat and work, and then which one's bigger in absolute terms. Let's see. What did I do wrong? Delta E is negative for endothermic process that performs work. Negative. I think those are wrong. Right? So that should be positive, and this should be negative. Yeah, I think those are reversed. Don't you think so? What about this one? Work is done on a gas. Work is done on the gas, positive. And it's exothermic, negative. So if this absolute value is greater than that one, the total should be negative. Right? These are reversed. It's wrong. Yeah. Need to fix that slide. Make myself a note. Or too far along. Yes, that should be reversed. Okay. All right, so now another concept. The concept of enthalpy. Enthalpy can be thought of as heat of a reaction. but it's not equated with Q. These are two different values. They use the same units of measure, of course, but they're derived differently. Q is accounts for all the heat that moves no matter what the reaction. And it also depends on what path was taken. Right? So it sums all the energy transfers, the heat transfers in the process. So if your system goes to here, and then it goes to there, and then it goes to there, and then it goes to there, and then it goes back here, the Q adds up. But if it goes that route for enthalpy, there's no change, because enthalpy is a state function. It doesn't care how it got there. Think of enthalpy, or delta H, as more along the lines of potential. Let's see. Do I have that in here? Maybe it's on the next slide. Whereas this is actual. This is potential. This is actual. Now, you can set up the conditions to where they're both equal. And that's what chemists usually do. That way you can measure the heat transfer in a reaction and equate it to enthalpy. Okay, so what are those conditions? When can you say that Q and delta H are numerically equal? And parenthetically, enthalpy and internal energy are both state functions, whereas W and Q are path functions. Okay, so you have to take my word for this one. Enthalpy is equal to internal energy plus any changes that occur to pressure and volume. Right, so pressure can change, volume can change. And now what we're going to do is use this relationship plus the equation of this one to set up conditions in which Q and delta H are equal. And then if you always adhere to those conditions, then you can run your experiment and determine delta H, because Q is the actual transfer of heat, and delta H is the potential that relates to that Q. Okay, so what do we need? We need the equivalence of this one, which is Q plus W, right? So now, enthalpy is equal to this one plus this one. If the process takes place at constant pressure, then we can bring this pressure outside as a constant times the delta V. Right? So we can say this, that, at constant pressure. Right, so we've done two things. We've equated this one, and we've set the conditions where pressure is constant, does not change. So, we also know that work is equal to minus P delta V. Right? So if we say this work right here, this value, we can substitute that for our W. Then we can say delta H equals Q minus P delta V plus P delta V. That one cancels that one. And under conditions of constant pressure, delta H equals Q. So the enthalpy equals the heat transfer measured as Q. pressure has to be constant. If you let the pressure vary, then all bets are off. Okay. So this just emphasizes the fact that if we let pressure, volume, and temperature vary for a gas, then we know that the values of Q and W will be different because of the way we calculate work and because of the way heat transfers back and forth. And if we let pressure vary, then Q is not delta H. Q and W are path functions. But delta H and delta E are state functions. And that's convenient because if we know the delta H for the products relative to some fixed standard and the delta H for the reactants according to some fixed standard, we can calculate the delta H for the reaction simply by subtracting the two. And it doesn't matter how they got there, right? Because it's a state function. Okay. Here's an example of a reaction. We're going to take propane and burn it and make carbon dioxide and water. And under these conditions, the enthalpy for that reaction is negative 2,000 kilojoules. So it's a huge amount of energy. Now, under what conditions do you get this many kilojoules? Well, under the conditions where you have 1 mole of propane being burned to use 5 moles of oxygen and produce 3 moles of CO2 and 4 moles of water. Those are the conditions. So you could write this, if you need a conversion factor, this is in terms of, for instance, 1 mole of C3H8. So that much energy per mole of that reactant. Or if you need something else, it would be that value per 5 moles of oxygen. Okay, so it just depends on what's required to solve a problem as to whether you say that in terms of this, in terms of that, in terms of that, in terms of that. Now, what you may see in some books, and I've seen it before, what they will say is this value per mole of reaction, which in my estimation means absolutely nothing. It's a worthless expression. I like the one where you actually specify which one pertains to that. Okay, so let's calculate the delta H in which 5 grams of propane is burned in excess oxygen. All right, so we don't have to worry about this because we've got plenty of it. We're going to use as much as we need, and we're only concerned with 5 grams of propane. C3H8 5O2 yields 3 CO2 plus 4 waters. And the delta H for this reaction is minus 2,221 kilojoules. And we're given 5 grams of that. Okay? So, in order to use this expression, we need to know how many moles of that we have. Right, so what do we need? Our conversion factor. Right, molar mass. So if we add up 3 carbons at 12.01 each and 8 hydrogens at 1.01 each, I get 4411. divide that into 5, and I get 0.1134 moles of C3H8. Now to convert that to energy, we just need our factor in terms of minus 2221 kilojoules per mole of C3H8. So this times that. And I get 252 kilojoules. Negative. Exothermic. Okay? Now, how do we obtain all these values? Well, you have 2 ways. You can either look it up in a book and do a calculation, or you can actually go in the lab and determine how much energy is produced by that reaction. Now, since we know that 1 mole of propane combusted that way produces a huge amount of energy, you probably want to take precautions or use a much smaller amount. Okay? But it can be measured. So calorimetry is the science of measuring heat. Calor is, I think it's Latin for heat. What's one of those, how many of them are there? Four signs that EMT looks for in assessing a patient. Calor is one, is heat. Right? Doler is another one. Forget what that refers to. There are 2 others. Ruber, color, and 1 other. It's been a long time since I've taught the course, so I don't remember. And I don't use it every day. Okay, let's see. I shouldn't have done that. Here we go. So in order to assess movement of heat, we need to be able to measure temperature. But we also have to recognize that different substances change temperature different ways in response to heat. And we call that heat capacity. So the heat capacity of an object is the change in temperature with change in heat. And if you have more of the substance with the same amount of heat, the temperature changes less. Or if the temperature changes the same for a larger amount, it requires more heat. Right? So this is a capacity factor. It does vary with the amount. And that's not very convenient. So we want to convert it to a intensity factor by ratioing it. Right? So if you ratio this to the amount that you have, usually in terms of grams, then you have specific heat capacity. Now it doesn't change as long as you have the same substance. That value will be in terms of, let's see, the energy required to raise the temperature. So the energy required is joules to raise 1 gram, 1 degree centigrade. Those are the units of your specific heat capacity. And you put a number here depending on the material. Is it water? Is it iron? Is it a gas? Those types of things. That's in terms of mass. Sometimes it's useful to express this specific heat capacity in terms of moles. So the molar heat capacity is in terms of joules per mole degree centigrade. Okay. Sometimes you might see this joules per gram K or joules per mole K. It's exactly the same number because the size of a degree centigrade is exactly the same as the size of a degree K. Actually, it's not degree, the size of K. They're the same. Okay, so back to calorimetry. If we mix two reactants at the same temperature and the resulting solution gets warmer, this means the reaction is exothermic. Temperature increases. And vice versa, if it gets colder, it's endothermic. And anybody that works in the hospital setting or as an EMT understands intuitively endothermic and exothermic reactions because they have cold packs and hot packs available. All you have to do is break the container inside, mix it with the water, and if it's a cold pack, it's an endothermic reaction. It'll draw heat from its surroundings. And if it's the other way around, it'll generate heat. So this is what our calorimeter looks like. Nothing fancy. It's just two styrofoam cups nested together. That's to provide the best isolation that we can for our system. So our system is in here and it's isolated from the surroundings. Now the system includes anything you add in here. The stir that's in there has a heat capacity and the thermometer has a heat capacity. So the total together is in the isolated system. But we're not going to use the stir. I've been using it, but it just adds complexity. And if you're careful with your thermometer, you can use your thermometer to stir things around. Okay, so that's the only thing that we're going to insert in there. We're not going to insert that. And I've made these things, and I keep them with me at Beckley, so I have to bring a box full over here. So what this does is it measures when we add two or more things together, it measures the change in temperature. So how do we relate the temperature to heat transfer? You need a formula. And there's your formula. So the heat transfer, we're back to using Q, is the specific heat capacity of a substance times how much of it is there, the mass, times a change in temperature, right? Remember, the change of temperature is always final minus initial. So that means if it ends up at a higher temperature, this value is positive. And if it ends up at a lower temperature, the value is negative. Okay? So this is going to be degrees centigrade. This is going to be in grams, which means this is in joules per gram degree centigrade. And when you multiply them together, grams cancel, degrees cancel, and you're left with joules for your heat value. Okay? That's just checking our units to be sure that they're all in order. Now, how do we know what this is? Well, you can look it up in a book. Right? There just lists and lists of the stuff. Or if you don't know what that is, then you need some way to measure the joules and the mass and the change in temperature. You calculate what S is. So how do we do that? Well, let's get some intuition involved first. Say we have 100 grams of water at 90 degrees and 100 grams of water at 10 degrees. Right? We know now, since they're both water, that the specific heats are going to be equal. Right? They don't enter in as a factor. And we have the same amount of each one. So what does your intuition tell you about what's going to be the final temperature? We're going to go from this one toward that one, and they'll meet in the middle somewhere, right? They got the same mass of the same substance, then you would expect them to meet exactly in the middle. So 90 minus 10 is 80, and halfway in between is 40 degrees movement. So 40 degrees from 10 is 50, and 40 degrees from 90 is 50. So they should meet right in the middle at 50 degrees. Okay. Now, what if you started off with 100 grams of water at 90, but you got 500 grams of water at 10 degrees? Where is it going to end up? Well, we'd expect that the 500 grams of 10 degree water would tend to weight it toward something less than 50 degrees, between 10 and 50. Right? But can we calculate what that temperature is? That's a rhetorical question. Yes, we can. So I'm going to give you the way to do it. Okay, in an isolated system, the Q, or the total, everything that happens in that system, everything that happens in Vegas stays in Vegas, right? Inside those styrofoam cups, anything that happens has to total up to 0 in terms of heat. Right? Any transfers, everything that happens in there, all the energy in that cup stays there. So if you do any calculations about individual segments of the contents of your calorimeter, they all have to add up to 0. Okay? So if you have something that you can calculate as Q1 happening, and then Q2 also happening, they have to add up to 0 because our system is isolated. All right? In this case, our Q1, well, we could just take them in order. Our Q1 has to do with this one right here. 100 grams of water starting at 90 degrees. Right? So this Q, based on our expression, our earlier expression, like that, has Q1 then would be, what's the specific heat of water? Well, they didn't give it to you, but I'm going to. Specific heat of water is 4.18 joules per gram degree C. And the mass is 100 grams. Right? They have to be the same units. And then times a change in temperature. Well, we know the starting temperature, 90 degrees. But we don't know the final temperature. That's our unknown. Okay? So there's our Q1 for 100 grams at 90 degrees. Now we need to add together to that, what's the Q2? Well, it's water, so it's the same specific heat, but now we have more of it. And then, what's the final temperature? Well, it's all going to come to equilibrium. The final temperature is going to be constant. Once it settles down, once we've mixed it well, and whatever change has taken place, then the final temperature is the same for both of them. But the beginning temperature for Q2 is 10 degrees. See? Okay? So now, all we have to do, since this equation is in terms of one unknown, we can solve for that unknown. So let's resolve this one. right? So since we've got an unknown here and a known here, we would say this one times that times that. So 4 times 100 is 418. Yeah, 418 times T sub F. Right? And then 90 times 418 is 3,762, but it's got a negative sign. And that's joules, right? Because the degrees canceled, the grams canceled, and leaves us with joules here. This one's, well, that whole thing is joules, but we still don't know what the temperature is. Now the other one is 418 times 500 times T sub F. So that's 2,090. 2,090 T sub F. And then 2,090 here times 10 with a negative sign is 2,090. Okay. So let me see if I did that right. This looks right here. 418 times 90, yeah, it's about 4,000. And then this one, 4 times that one. Because it's times 1,000 would be 4,000, and then half would be about 2,000. Okay, that's good. And then 2,000 times 10 was 20,000. Okay, so that's ballpark, makes sense. So now we resolve, we combine this one with this one, 418 and 2090, and that's 2,508. Times T sub F, that's these two, and then combine these two, so that's 20,900, and then 3762, change the sign because it's negative, and that's negative 2,462, still equal to 0. Okay, so we need to put this one on the other side and then divide it by this number. So now it becomes positive on this side, 24662 divided by 2508 equals 9.8. That's not right. Calculation error. So let's check our figures. 4.18 times 100. 418. 418. Have a piece of that. And then times 90. Okay. Now, this one and that one, 200 is 5852. 520. So this should be 5850. And this should be 5850 divided by 25. 23.3 degrees C. Close enough. Okay, now that jives with our intuition. It said it would be between 10 and 50. Before 9.8, that was off the map. It can't be lower than 10. It's got to be in between. So that didn't matter. That didn't match with reality. They're roughly 23 degrees. That's how you do calorimetry calculation. Everything that happens in Vegas is equal to 0. Now, what happens if you have two different specific heats involved? You just change the S value, right? For this one, 50 grams of water at 10 degrees, that's going to have an S of 4.18. But 50 grams at 90 degrees for an iron ball is going to be 0.45 for this one, okay? And you just do the same calculation without the mistake and determine the final temperature, right? And if you go through that whole thing again, you end up with 18 degrees as your final temperature. Okay, now, suppose we want to investigate a reaction, but for safety reasons, we'd like to predict what to expect, right? Is this going to be a violently exothermic reaction? Well, we don't know. But the reaction's never been done before. There's no data on it. We can use Hess's law. Hess's law takes advantage of the fact that delta H, or enthalpy, is a state function, which means it doesn't matter how we get there. We could get there by this reaction plus this one plus this one plus this one to get to our target. And if we know the heats for each one of these, we can calculate the heat for the target reaction and determine whether it is going to be dangerous or not. Or maybe we haven't even decided we want to do the reaction. We just want to play around with the numbers and find out, right, is this a reaction that I really want to do? And a piece of the puzzle is the enthalpy. So Hess's law says that we can calculate the delta H based upon other reactions that can be summed together to give you the delta H for your target reaction. But there are some rules, of course. Say this is our target reaction. Nitrogen gas plus oxygen gas yields nitrogen dioxide. And let's say, for argument's sake, that somebody did do that reaction and they found the delta H was 68 kilojoules. Okay. We want to see if Hess's law works, right? So we're going to take these two reactions and see if we can combine them in such a way to give us that reaction. Well, see, this one's written. There's our arrows. So nitrogen's on this side in one of them. That's good. Oxygen's on this side. That's good. And two NOs are on this side, but there's none up there, right? So that means that NO has to cancel out in the process. So this reaction has two more NOs over there. Okay, so those cancel. And this one adds an extra oxygen, which gives us our two oxygens. Right? So one nitrogen, two oxygens, and the product of this reaction is NO2. Now, as written, the enthalpy for this reaction is 180. The enthalpy for this one is negative 112. We add those two together, we get 68 for our target, and it agrees with the actual determination. So the delta H, Hess's law, is at least confirmed in this case. Now, what do you do if you want to use reactions that aren't written correctly so that you can add them up, right? This just illustrates that it doesn't matter how you get there, you still have the same difference in heat.
Hess's law illustrates why enthalpy is a state function. For example, we want to determine the enthalpy change for the combustion of graphite to carbon monoxide. Imagine that the reaction takes place in two separate steps. Step 1 is the combustion of graphite to carbon dioxide. Step 2 is the decomposition of carbon dioxide to carbon monoxide. The net result is obtained by adding the two steps and canceling out like terms. The enthalpy change for step 1 is negative 787 kilojoules. The enthalpy change for step 2 is positive 566 kilojoules. Therefore, the desired enthalpy change for the net reaction is the sum of negative 787 and positive 566 kilojoules, or negative 221 kilojoules.
Okay. So, what do? If we have to reverse the reaction to get things on the correct side of the arrow, you just reverse the sign of your delta H, right? Because if it's exothermic in this direction, it's endothermic in that direction. That just means change the sign. If, however, you have an equation where you don't need everything that's in the equation, like say you need half of it. So you multiply everything through by a half. Then you just do the same thing to your enthalpy. Take half of it. Sometimes you have to do both. Reverse it and multiply it by some factor. So just do them one at a time. Change the sign, multiply by the factor. And as long as your equations add up to your target, then you can add up the enthalpies as calculated for the changes. So in this case, suppose we want to calculate the delta H for this. This is our target. So nitrogen plus water yields oxygen plus ammonia. If we use this one here, ammonia is on the wrong side. It needs to be on the other side. So we need to reverse it and change the sign. But we need 4 here, right? So after we reverse it, we need to multiply the whole thing through by 4. Which means we multiply this negative 46 now by 4. Likewise, this water is on the wrong side. So we put it on that side, and we need 6 of them where we only have 2, so we multiply by 3 and change the sign. So a positive 484 times 3. And then we add them together in their new configuration to see if they give us the target. If you get the target from those changes, then you can add these together. Okay, so this one has taken into account, putting the, excuse me, there we go. All the changes where we change the sign and we multiply it by factors, and this was given, and add them together, and you get your delta H for this reaction based upon the summation of those two. That doesn't have to be 2 equations. I mean, it could be 3, 4, 5, whatever it takes. It can get really complicated. Okay. Now, suppose someone says, what's the standard heat of formation for this compound? You can look it up in a book, in a reference manual. But it's not going to tell you the reaction that is referenced for that value. It's just going to say, what's the standard heat of formation for ammonia, say? This is for argument's sake. What's the delta H for that? All right. It'll give you a value, but it'll just say delta H, and this is standard conditions. Delta H of formation for that compound. That's it. It won't tell you anything else. In order to use it, you need to know how that was formed, right? So the key is it's always in terms of 1 mole of product. That's the product, like that. And then this value for that product. Now, how do you get there? You get there by using standard forms of the elements. So you need nitrogen in its standard form, which is a gas, a diatomic gas. And these standard conditions are temperature is 25 degrees centigrade. Pressure, if you have gases, is 1 atmosphere. If you have a solution, if you need a solution, then the concentration is 1 molar. Let's see, temperature, pressure, concentration. And then hydrogen, you need its standard elemental form. Hydrogen gas, nitrogen gas. Now, when you balance this expression, this equation, can't touch that. You know, who was it said can't touch this? MC Hammer, that's right. See, can't touch that. 1 mole here. So that means you're going to have to use fractions over here. Right? So in order to get 1 nitrogen, you need half of this one. Okay, that takes care of nitrogen. You need 3 hydrogens. So you need to take half of this and then times 3 to get 3 hydrogens. Right? Half of a hydrogen molecule is 1 hydrogen, then times 3. There you go. So that's the expression that this refers to. Let's see if I got them right. 1 atmosphere pressure, 1 molar concentration. Pure substances, liquids or solids. Right. So if this was gold leading to some compound, it would be AuS, or solid, because it's solid under these conditions. Okay. All right. So now that we understand what the standard heats of formation are for these compounds, we can use those values to determine the delta H for a reaction in terms of reactants yield products. Right. So what we need is the delta H for that reaction under standard conditions is just the sum of the product heats of formation. Right. You know, big sigma means sum. Okay. And then you have to multiply by the coefficients for each one of the products. Right. So it'll vary depending on what it is. And then the delta H of formation for the products here minus the delta H of formation for the reactants. Okay. So in this case, for this reaction, what they've done is they've kept the reactants on this side, right? So the reactants have to be negative because of this sign here. So they're lining them up with these. Now, the one thing that I didn't tell you was the delta H of formation for elements is 0. Delta H of formation only works for compounds. Elements in their standard state are always 0. So here we have oxygen in standard state, there's its 0. The rest of them have values. Methane has a value, carbon dioxide, water has a value. And if you just sort of mentally say, all right, here are the reactants, so they're the negative ones, they go over here. And these are the products, they're the positive ones, they go over here. I think it's confusing to do it that way, but who am I to argue with publishers? Okay. So yeah, these are the rules again. Right? Here's your formula. It's like this. And here's an example. So if we want to find the enthalpy for this reaction, the nice thing is there's an element, those are zeros. So you really only need this one times 2, so that times 2, minus this one times 2. Okay. And then you can calculate the enthalpy, the standard enthalpy of that reaction. That's why that little zero's there. Standard conditions, that's the enthalpy for that reaction. All right. I don't know if I want to get up on my soapbox or not. I'll try to keep it apolitical. The various forms of energy that mankind has used over the centuries begins with very simple things. What's available? Well, let's see. We have wood available. Used to be a lot of it. There's a lot less now than there was. In fact, one commentary I read was that Spain at one time was covered in forests, right, from coast to coast. And over time, they depleted them, and now it's makes good scenery for spaghetti westerns. So the Italians go over to Spain and shoot their westerns there because it looks like the American Southwest, because there are no trees. Now, some of it was burned, right, for energy, but some of it was also used to build the Armada, build the ships they made. I don't know which one is responsible for deforestation. But wood used to be the principal form of energy for anything that man did, whether it was for cooking, heating their homes, or industrial purposes. In fact, initially, wood would be heated, would be pyrolyzed into carbon or charcoal before it would be used to make steel. That was before we located a ready source of coal. And then we went through a coking process. But wood was first. And then after wood came fossil fuels. Right, so the discovery of fossil fuels is the single most important factor for the Industrial Revolution. Right? Up to that time, we had hydropower and we had wood boilers. Right? They were very inefficient. Then you had to go farther and farther and farther afield to find wood because you kept cutting it down around your factory. And if you used hydropower, before we had dams and electricity, you had to build your mill or whatever factory you had on a river or stream and set your water wheel in the stream. And then mechanically run off of that wheel with belts and pulleys and whatever. Then, of course, when we figured out how to convert a spinning turbine under pressure from water into electricity, then you could move it anywhere and just transfer the electricity to wherever you needed it. With the help of technology developed by Nikola Tesla and his benefactor, George Westinghouse. And that was a huge controversy developed here because Nikola Tesla first started working for Thomas Edison. And they had a falling out because Thomas Edison promised Nikola Tesla a certain amount of money for doing this, and this, and then he reneged on the deal. So Tesla said, bye-bye. He went to George Westinghouse, and they blew Edison away, because Edison was for direct current. And Tesla had this idea that alternating current could be sent farther. In fact, it was. Direct current could only go a couple of miles, so you had to have generating stations built along the way. And so after fossil fuels, we came across nuclear power. Right? So nuclear power, the advantage to nuclear power is once you fuel your reactor, it's good for 20 years before you have to refuel it. Then, of course, you got to figure out what do I do with the waste. But if you ever run into a global warming hysteric who thinks that man's the cause of all evil, just ask them, all right, if you don't want us to use fossil fuels anymore, where do you stand on nuclear energy? Because it doesn't produce any CO2. And if they're against nuclear too, then you can call them a liar to their face. Okay, so this is like a history. So we started off with wood, and then over time, we transitioned toward coal first, and then we found that petroleum and natural gas was easier to get at, cheaper to get at, and just as useful. So we still use some coal, right? But the petroleum and natural gas still make up the lion's share of fueling our economy. Cheap energy translates into good economies. When energy gets expensive, economies tend to crash. So the fact that America now, the United States, is energy independent is a good thing, because no other country can hold us hostage. If we're going to crash our economy, we have to do it to ourselves. and there are a sufficient number of Democrats, well, they used to be, well, they start off with 27 Democratic candidates for president. They were all a bunch of socialists, and all of their plans would crash our economy. So I can only hope that once they're down to what, Slow Joe and Crazy Bernie. So whoever comes out of that fight, I just hope they lose in November, because if they get their way, we're in for a recession again, maybe even a depression. Okay, so what is it about the Earth's atmosphere that gets hysterics all wound up? Well, it's based upon the concept of global warming, that is trapping energy that is either produced from within the planet or received from the sun and re-radiated at longer wavelengths, which is true. And those longer wavelengths, while the shorter wavelengths can penetrate the atmosphere, the longer wavelengths get trapped by things in the atmosphere. So what are those things in the atmosphere? Well, there's some CO2, right? We've noticed it's increased over 400 parts per million now. Right? When they first started measuring it, it was in the neighborhood of like 350. And so it has increased. But there's a whole hell of a lot more water in the atmosphere than there is CO2. And while water may not be as efficient at trapping energy as CO2 is, there's so much more of it, it has a major impact on whether or not energy is re-radiated into space or trapped. And then, of course, you get the added complexity of, if water's in clouds, then it reflects the energy before it even gets to the Earth. So the moral of this story is the Earth's climate is too complex to adequately model even on any supercomputer. They just don't have the models that can predict into the future more than 20 minutes. And they're saying 100 years down the road, we're going to be 4 degrees warmer and the seas are going to be 100 feet high. So yeah, I say, you do what you have to keep your government grants. I've got a cartoon on my door at my office in Beckley. It's Dilbert cartoon. I should put it in here. But it's a parody of Michael Mann. You know who Michael Mann is? He's a climatologist at Penn State that came up with the hockey stick model. Right? So what he said was, here's time, and here's temperature. Okay? And for the longest time, Earth's climate was very stable. Just goes along like that. And then when man started industrializing, it goes, there's your hockey stick. Right? Well, people started calling him on it. They said, wait a minute. It wasn't flat for all that time. Right? First of all, it goes like this. Right? Even here, it goes like that. But there are two major anomalies back in here that he just threw out. He says, it doesn't fit in my model, so I just threw that data out. One was the medieval warm period. That. The other was a little ice age, like that. Right? So you got to figure, and this was before industrialization. So you got to figure, if it happens here, it's got to have happened back here. So the Earth's climate, first of all, the Earth's climate does change. Right? That's a fact. But whether or not man causes it is the argument. Man may have an impact, particularly on regional, local microclimates. Like if you deforest an area, temperature is going to rise. That's a fact. Or you build a city, they call them heat islands, right? Every sailplane pilot knows about heat islands. So if the air traffic control will let them, they just fly close to a city and they just ride the currents and go that. And then where do you place your measuring devices? Right? The temperature measuring devices have been just placed willy-nilly. Right? So the data that you're getting is bad data. So try to base a theory on bad data, it just never works. All right, so I need one of Michael Bloomberg's boxes to stand on. I need sub-boxes. So this is the thing. Now, we have observed warming on a global scale. It happens with our sister planet, Venus. Right? Internal heat from the planet plus solar radiation is trapped in that planet's atmosphere. But the content of its atmosphere is massively laced with carbon dioxide and sulfuric acid, which form greenhouse gases. And at those concentrations, they do have an effect, right? But there are no people there to blame it on, right? So the hysterics only peripherally refer to Venus, and then they set it aside to attack Earthlings. Okay, so what are potential sources of energy, right? How are we going to keep the ball rolling? Well, there are technologies for converting coal into gasification, right? And in the process, you remove a lot of the impurities, right? And natural gas is less polluting in terms of CO2 than coal is, right? But then you get this solid waste and you got to do something with it. Right? So you'll have ash that comes from the coal, and you have the sulfur compounds that are trapped and removed from coal to produce the gas. And that's fine. You know, if it's economically viable, I say go ahead with it. You know, if you can make a buck, do it. I just don't want government subsidizing it. Hydrogen as a fuel. That's like the holy grail. Hydrogen as a fuel. If you've got a cheap source of electricity, you can split water into hydrogen and oxygen and store the hydrogen and use it to drive your engines or run your fuel cells, right? And what do you get as a product once you start running? Water. Hydrogen and oxygen make water. That's it. No CO2. So they ought to be happy about that one too. The problem is we haven't produced an efficient fuel cell that it can be safely incorporated into vehicles and cheaply incorporated. That's another thing. Economics is always something they ignore. Plus, we don't have the infrastructure. Right? We have the infrastructure for gasoline and diesel now. Right? You'd have to build an entire new system for hydrogen. Other energy sources, oil shale. Right? Where does that come from? Well, it comes from deposits that were previously inaccessible until fracking came along. And fracking made these oil shales available. They also made natural gas available. You just shatter the formation and out it comes. That's why we're now a net energy exporter. Ethanol produced from biomass. Well, in this country, the biomass is corn. The problem is it costs more to produce a gallon of ethanol than it does to grow it. I mean, to produce it by growing it and converting it, than it's worth on the market. So that's why it has to be subsidized. Okay. If the government took away its subsidies, that industry would collapse overnight. Other countries make it from different types of biomass. Brazil's been doing it for ages. They make it out of sugarcane. But it has to be subsidized there too. Plus, ethanol doesn't have as much energy in it as octane does. So when they mix ethanol in with your gas, you're getting less energy. The theory is that when you put ethanol in your gas, ethanol is that. So you're adding oxygen, and theoretically, it provides more oxygen to burn the fuel and produces less pollution. Methanol also is a burnable fuel. Seed oil. You know, the diesel engine, I forget diesel's first name, but it's the name of the guy who invented the diesel engine, was designed to run on vegetable oils when he first produced it. It only later became converted and modified so that it would run on petroleum-based fractions, the diesel fraction from crude oil. That's it. I've said all I need to say about that. So how are we doing on time? Ooh, we're finished an hour early. I'd go for that, especially since it's supposed to be snowing outside. But I'm not sure what the temperature is on the mountains. I might risk it. I'm feeling adventurous today.